Okay. Okay. Now it has started. Okay. Alright, so welcome to part 2. So we have covered some basics of convexity, convex hulls, and systems of linear inequalities, right? And what we discussed, perhaps the most important thing we discussed, was the Weyl-Minkowski theorem, which states that any convex polytope, for any convex polytope, there is a system of linear inequalities that describes that polytope. In other words, a point lies in the polytope if and only if it is a solution to that system, right? So that naturally raises the question is whether there is a linear inequality description of the perfect matching polytope. So that's basically what we are discussing next. Linear inequality description may also be called an LP formulation, a linear program. Yeah. So that's the next goal. Alright, so yeah, so this was a major open problem. Back in the day, people had necessary conditions for the perfect matching polytope, but well, necessary inequalities, if I may call them, but it wasn't clear how to make them sufficient, how to make the system both necessary and sufficient. So let's discuss some necessary conditions, some very easy necessary conditions, right? So let's draw our standard graph. I should just start calling this a standard graph. Okay. So now let's think of a perfect matching and the corresponding vector. Well, the corresponding vector is a 0, 1 vector, the corresponding incidence vector. It's a 0, 1 vector with ones in the entries that correspond to edges that belong to the perfect matching. Zeros everywhere else. Well, if you take a bunch of such vectors, there are 0, 1 vectors in particular, and you take their convex combinations, will you ever get a negative entry? You won't. That's clear. So it's clear that whatever is in the perfect matching polytope needs to satisfy non-negativity. Okay, that's clear. So so let's say x is a vector in the edge space. If x belongs to the polytope, to the perfect matching polytope of the graph G, by the way, I've written the definition of the perfect matching polytope formally here. Right? If it belongs to the polytope, what is clear is that the vector is non-negative. In other words, every coordinate is non-negative. This is clear. Okay, that's very trivial. What else can we say? Let's think about, well, it's a perfect matching. If I look at any vertex and if I sum up the numbers incident at that vertex, what do I get? What is the sum at each vertex? It is 1. The sum at each vertex is 1 because it's a perfect matching. If you take convex combinations of such vectors, remember in the convex combination definition, the coefficients are non-negative and they add up to 1. Then can you see that in any convex combination, you can say something interesting about the sum at each vertex? Right, so that's the question I want to ask you. If I consider the sum at each vertex, this is where that notation will help us, right? That dot product notation. If I consider any vertex and I consider x of partial of v, this is basically just the sum of the x values of the edges incident at v because of the way we defined x of capital F, right, for a set of edges. Then what can we say about this sum? And think about it and I will come and talk to you. Right? Some of you may already know that is fine. But if you haven't seen this before, then try to see if you can figure this out. For any vector in the polytope, what can you say about x of partial of v, where v is any vertex of the graph? Okay, anyone else? Just write it out. If you write it out, you will see. Remember the lambdas sum to 1. That is very crucial. The lambdas sum to 1. Oh, sorry, the alphas. Sorry. In my mind, they are lambdas, but in Lucas Murthy, they are alphas. Yeah, thank you. Yeah. Right, so your x is basically something that looks like this. For some set of perfect matchings, well, you can take all the perfect matchings. It will be alpha 1 times the first perfect matching incidence vector, alpha 2 times the second one, and so on. But what you know is that all the alphas, they sum up to 1. Right? You just have to simplify the equation and see what you get. And while you all are working on that, well, some of you, I will give you a nice vector, and you can try to see if you can write it as a. I'll give you a couple of examples to work out. So this is K4, and here is a vector 1/6, 1/3, half, 1/6, half, 1/3. Check if this is in the perfect matching polytope corresponding to this graph K4. Right? If it is in the polytope, you should be able to write it as a convex combination of perfect matchings. Right? There are only so many perfect matchings in this graph. Right? And I'll give you one more example. I'll draw K33, but in this way. Yeah. So half, 1/6, 1/3, 1/6, 1/3. These are the two edges incident here. Half, 1/3 here, and 1/3, 1/3 here. See if you can check for both of these examples. It will take some time, but that's fine. Okay, and okay, I'll come and talk to you. Yes, that's right. Yes, that is correct. Can you make it stronger? Mhm. Right. That's okay. You're right. So the answer is it should be equal to 1. You know that the sum of all the alphas or the lambdas, whatever you call it, that is equal to 1. The sum of all, because it's convex. No, the sum of all alphas, right? You're basically taking the set of all perfect matchings. You're multiplying the first one by alpha 1, second one by alpha 2, so supposing there are 10 perfect matchings, you know 10 alphas. You know that the sum of all alphas is equal to 1. Yes. It will not be any perfect matching. Okay. Anybody else regarding the first point? What can you say about x of partial of v? Yeah. Yes. By assuming. Yes. 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 No, what we have is a convex combination of perfect matches. Right. So, for example, the earlier example I drew that when I put some the second drawing, when I put halves on a quaternary and I put one below. Right. So, for example, that vector is in the polytope because it is just half times one perfect matching into half times another perfect matching. So now we are not considering this. Of course, in perfect matching, it is clear that x of partial of b is equal to 1. But now we are taking on the formulation. So we have basically, supposing your graph is 10 perfect matching, and we multiply the first one by alpha 1, second one by alpha 2, and so on, and I add up all these. So I get sum negative. If all the alphas are non-negative, and the sum is equal to 1, then it's a convex combination. That is in the back. That's what I was saying. Now I'm giving you a vector in the polytope, so you cannot give perfect matches. It is a convex combination of perfect matches, which are defined below. Right? It's basically the summation of alpha n times incidence vector of some perfect matching over all basic. But you know that all alphas sum to 1 and each of them is non-negative. So using that fact, what can you say about x of partial of b? No assumptions. The edges that are not in a perfect matching will simply be 0 and all vectors. What will matter is the edges that are in some perfect matching. Okay, then discuss. Yeah. That is what I kind of did last night. So you can't really subtract because then it won't be the polytope anymore. Basically, what you're saying is that you will calculate a certain perfect matching on 6 times. Now, please not I don't need that. At least I have to do 4. This will form the part of that. But in this graph, since there are perfect matching, there is no perfect match, but I will still have that actually. Yeah. First one, yeah. Okay. Alright, so I hope that you all have convinced yourself by now that this is actually equal to 1. And if you think you are not fully convinced yet, that's okay. I'll put it as a DIY. Make sure you work out the entire details and you're not just assuming it. Right? Yeah, so there is some stuff that is a bit uncomfortable, right? It's not what we normally do, but that's okay. Some amount of discomfort is necessary to learn. Yeah. Okay, so these two are necessary conditions for a point to be in the perfect matching polytope, for a vector to be in the perfect matching polytope. Yeah? Are they sufficient? This is, right? I can see some of you nodding in the negative. Is this if and only if? If it is if and only if, that would be great. Then we are done. Right? Then we have a complete description of the perfect matching polytope, and it turns out to be very trivial in some sense. It turns out to be very straightforward. Okay, if you think it is not sufficient, they are necessary conditions. If you think they are not sufficient see if you can come up with a graph, and I will come and check. Yeah, see if you can draw a graph and a vector. So what do you want? If you believe this is true, try to prove it. If you believe this is not true, if it is not if and only if, then see if you can come up with a vector that satisfies these conditions, but it should not belong to the polytope. And for that also you should have a proof why it does not belong to the polytope. Right? And I will give you a hint that there is such a, I'll give you a hint, the answer is on the board. Okay. Not the board that is visible to the audience in YouTube, but the others. Okay? No, it is there. It is there. It is. 4, right? Okay. I won't check it right now, but if it's 4, then it's probably correct. Yeah, it looks something like this. Yeah. This one is here. This one is here. There are 2 of these and 1 of this. Yeah, this is correct. Yeah. I didn't check all the details, but yeah, looks correct. Oh, by the way, we'll be getting close to 4 p.m. soon. So if anybody has to leave at 4, just let me know so that I'll try to wrap up soon. Otherwise, we may go until 4:15 or something because we started late. No? Okay. And while we are at it, let's try to figure out this example. Right? So, looks like most of you have figured out this example. This example is quite easy to see that this vector is in the perfect matching polytope for this graph K4. Right? So, can we come up with alphas? We have 3 perfect matchings. It's K4. There are 3 perfect matchings. That's easy. So, I have 3 colors here. Somehow pink is missing. Okay, so we'll take blue, the blue perfect matching. There is the orange perfect matching. And there is the yellow perfect matching. And in this case, it is quite easy to see that you take the blue times 1/6, the orange times half, and yellow times 1/3, and you will get exactly this vector. Well, that's how multiplication and addition works in this very simple example. And what is interesting is that half plus 1/3 plus 1/6 is actually 6/6, which is equal to 1. So this is easy, right? This is simply 1/3 times m1 plus 1/6 times m2 and half times m3. Think of each of them as a 0, 1 vector. I'm not going to write down the vector. That's what this is. Yeah? So therefore this is in the polytope. Right? All the coefficients are non-negative and all the coefficients sum up to 1. This is in the polytope. Okay, this one is straightforward. And this is also in the perfect matching polytope of this graph. This graph is K33. But if you are trying using 3 perfect matchings, I have a feeling that it may not work. K33 has more than 3 perfect matchings. Anybody has any idea how many perfect matchings K33 has? Each edge belongs to how many perfect matchings? In K33? 2. Therefore, there are how many perfect matchings? 6. Right? There are 6 perfect matchings. You don't need to use all 6. Well, maybe you can use all 6. By use, I mean non-negative, positive coefficient. if you are putting the coefficient as 0, you are not really using it, right? So turns out with 4 perfect matchings you definitely can. That is the solution I found last night, right? So I'll just give you the express as convex combination of k perfect matchings. My guess is that k equal to 4 works, but I don't know about other values of k. I didn't try. Yeah, and of course you can just take 0 with the other perfect matching, so it is therefore a convex combination of all perfect matchings. You don't need it. Yeah. Okay, cool. But now what about this? Is this if and only if? And if you think the answer is no, see if you can draw an example along with the vector, right? So graph along with the vector. If you have a graph that does not have a perfect matching, good. Then make a graph which has a perfect matching. Assuming you know this. Oh, this one. But what about this one? Oh, definitely. That you know.
I never worked from the details until today.
Okay.
Oh,
yeah.
This.
Yeah, I mean this. If and only if.
That time.
Okay. When you come up with a graph and a vector, the vector should be non-negative and it should satisfy this constraint. I'll give it a name, by the way. Yeah, so these are of course called the non-negativity constraints. These are called degree constraints. It's like degree. The degree of each vertex is equal to 1. But we will also call them one regularity. I'll call them degree constraints, or I'll call them one regularity. Sum at each vertex is equal to 1. In that sense, it is a one regular vector on this graph. Yeah. So can you come up with a, so I'll tell you the answer is no actually. In general, the answer is no. Therefore, see if you can come up with a vector, a graph and a vector that satisfies, that is a non-negative one regular vector, but it does not belong to the perfect matching polytope. Okay. In fact, the simplest example is actually a graph that does not even have a perfect matching. But you can still make such a vector, which would be absurd, right? Because if there is such a vector, but there are no perfect matchings, that means the perfect matching polytope is, it is a convex set, which is the empty set. So, but there is a vector. The vector is non-negative and one regular, but the perfect matching polytope is empty. Therefore, the vector cannot belong to the perfect matching polytope. So that turns out to be the smallest example. See if you can come up with a very small graph. No perfect matching in the graph, but there is a vector that is non-negative and one regular. now see if you can come up with a graph that has a perfect matching but still has such a vector. Okay. Alright. Yes. So you were saying that this vector has this property. It's non-negative, it's one regular. Why is it not in any perfect matching? Why is it not in the perfect matching polytope? Sorry. For the perfect matching, you should put 1 1 everywhere. Yeah. Yes. Yeah. That's correct. But can you come up with a reason related to this cut? Yes. Why is it not in the polytope? Are you convinced by that? Okay, see if you can come up with a more convincing argument. Okay? Yeah, which vector? Which one? The orange one. It's not negative and one regular. Okay. No, so we want a vector that doesn't belong to the polytope. No, it doesn't. You're allowed to use fractions, no? You can put half, 1/3. So I wanted to satisfy these two conditions. Yeah, one regularity just means that the sum of the labels at each vertex is equal to 1. So the labels need not be integers. The labels could be any numbers. This is not 1. Then why is it not in the perfect matching? Yeah? You have a convincing reason? Anyone else? So see if you can try with this example. For this particular example, K3, can you come up with a vector that is non-negative and one regular? If you can come up with such a vector, then you can already see that this is not if and only if. Because there are no perfect matchings, the perfect matching polytope is actually empty, so that would be a problem, right? Then the vector cannot belong to the empty set. Right? That would be a problem. That's okay. That is a perfect matching. So that's why it is in the polytope.
But it's the constraint is working.
it's a perfect matching only. Yeah, it is in the polytope also. Yeah, it satisfies the conditions. It must be registered as well. Yeah. But in the same we have something else. Some other vector. Yeah. It should not be in the yeah. You see this one. Now can you do something similar? What is the problem with this being 0? This is about so you're saying that all these values are 0. Why is that a problem? Why does that prove? It cannot be a linear combination of converse combination. Sorry, because every person mentioned it needs at least one is from this kind. Yeah, did you find the other one? Right, so everyone can see that this one, you just put a half everywhere. This is a non-negative one-regular vector. The graph has no perfect matchings. Therefore, the perfect matching polytope is the empty set. Therefore, you have a contradiction to the other direction. You have a vector that satisfies this, but clearly it cannot belong to the empty set because nothing can belong to the empty set. Right, so that one is fine. But now using the same idea, you can construct an example that has a perfect matching. Not only does it have a perfect matching, it is matching covered. It is our so-called standard graph, right? And now you put a half on all the triangle edges. This is a non-negative one regular vector where I don't put anything, I mean 0. Right? You can see that the sum at every vertex is equal to 1. But this vector does not belong to the perfect matching polytope. That is something you need to convince yourself. Why does it not belong to the perfect matching polytope? So this vector does not belong to the perfect matching polytope. Oh, sorry, not the right notation. Poly of the triangular prism. Right? Does everybody see why it does not belong? Yeah? You basically pay attention to some cut. Life is mostly about cuts. So you look at this cut and you observe that every perfect matching meets this cut in at least one edge. Therefore, in every vector corresponding to a perfect matching, the sum of the corresponding entries of these three numbers will be at least 1. Therefore, in the convex combination of such vectors, the sum should be at least 1. Right? So that's the problem, right? If this is my cut C, then M intersection C is at least 1 for each perfect matching, and that means that the X along this cut should be at least 1 for any X in the polytope. But for this vector, it is 0 plus 0 plus 0, which is not at least 1. That's a contradiction. Right? Okay, great. But now this is very interesting. This example actually tells you what you might want to do in order to fix this. We want to get if and only if statement. Turns out this example has what it takes. We looked at a particular odd cut. And we observed that every perfect matching meets this odd cut because it is an odd cut in at least one edge. If there is a perfect matching, well, if there is no perfect matching, statement is still vacuously true, right? So every perfect matching meets every odd cut in at least one edge, and therefore the sum along an odd cut in any convex combination of perfect matchings should be at least 1. So therefore it was natural at this point, the way we have discussed, to add one more condition. For every odd cut, the sum is at least 1. Turns out if you do that, then you actually get if and only if. That is what Edmonds proved. So for every odd set of vertices, this is at least 1. For all odd S subset of V. By this I mean all subsets of the vertex set that have odd cardinality. Right? And now it turns out that this is actually if and only if.
For the last constraint?
Yes, the last constraint, they are generally called the odd set constraints or the odd cut constraints, or we may also call them Edmonds constraints. I'll use all these names. Odd set constraints, odd cut constraints, or we may simply call them Edmonds constraints. This is what Edmonds proved in 1965. The fact that the two examples we looked at are non-bipartite is not a coincidence. It turns out for bipartite graphs, this is actually if and only if, even without this diy, that the first two constraints imply the third type of constraints, that is the diy. So for a bipartite graph, every non-negative one regular vector satisfies Edmonds constraints. So in the case of bipartite graphs, you really don't need to work any harder. The two obvious conditions, non-negative and one regularity, they turn out to be necessary and sufficient for membership in the polytope, in the perfect matching polytope. However, for non-bipartite graphs, that is not the case, as we have seen through two examples, but you can make many more examples. However, if you add these constraints, then you are good to go. Okay. And therefore, this may be regarded as what people call a linear program for perfect matchings. This is a linear program, and of course we haven't proved the Edmonds theorem, so that is what we will do next. We will see a proof of Edmonds theorem. I have seen multiple proofs of Edmonds theorem during my PhD, and since then but the proof that is in Lucchesi-Murthy is really new for me and I found it very interesting. So I'm going to present that. In fact, I sent a couple of clarifications to Claudio, and yeah, I'll mention those when we discuss. But yeah, it's a really cool proof, and we will see that in the. I was hoping to make some progress in the proof today. That is clearly not possible. We will do that on Monday. Yeah. Tomorrow we won't have a lecture. Tomorrow I have to attend the department meeting. Yeah. Okay. Any questions or concerns regarding anything we've discussed so far? If you are finding all of this rather non-trivial because there is a lot of thinking that is not what you're used to, that's fine. Just try to work out a lot of examples and spend some time on the basics, right? Even things like this, that the sum is equal to 1 for each vertex, make sure you've worked out all the details because you really have to use the fact that this is a convex combination where the coefficients add up to 1. That is crucial, right? Okay. Alright, if there are no questions or concerns, we meet on Monday. Have a nice weekend. Thank you.